Welcome, everyone. I'm Alex Barnett, and I'm really delighted to welcome you all here to Dartmouth for this week of mathematics. And I'd like to just first introduce some of the other organizers, who I'd also like to thank. Adrianna Gillman, who's at the back there. So Minyan Cho, who's waving his hand here. And the fourth organizer is Leslie Greengard, who will be coming in on Wednesday afternoon. So it should be here in time for the banquet. So, and I'd also like to thank Tracy Maloney, who's up in the math department, who makes this whole place work and has done a tremendous amount of work at the conference, and their assistant, Amy Potter. You probably met both of those. Both of them, if you went up there this morning. So we have a really amazing bunch of people here, an amazing opportunity to learn as well, and learn some really great new techniques that Per-Gunnar Martinsson is one of the main pioneers of. So one thing you should all try and do is swap ideas. That's one of the goals. So the afternoons, we have coding sessions in some of the afternoons, but also you should all talk to each other and talk to Gunnar and have lots of senior and junior interaction. And that's why we're all eating together. Those of you who are a funded participant, the idea is we all go to meals together and chat. And those of you who aren't are welcome to come and join in, but you have to pay. Sorry. We had way more applicants than we were able to actually use the funding for, so I think that's an exciting thing. And thank you for those of you who came as well. We have people here from all over the world, Japan, Saudi Arabia, Russia, and so that's very exciting. And so I'd like to thank NSF for the majority of the funding, but we also got funding from the math department, the Dean's office here, and from the Air Force Office of Special Research. So I think that's everything. You all have the schedule, and I think we're delighted that this all worked out. And Gunnar is someone, a researcher and educator that I really admire, and he's a great collaborator too. And I'm very excited to be able to, for us to be able to bring him here and teach you a fabulous bunch of stuff. So with that said, over to you, Gunnar.
Thank you for a wonderful introduction. And I'll do my most important slide first. I'll double up on the thanks to everybody who made this possible. So many thanks to the organizers, to Dartmouth College, the math department, to the NSF. And as a researcher, the most fun thing we do is talking about our work. And I get excited when I get invited to give a half-hour talk or 1-hour talk. So 10 hours is really extraordinary. So I'm most profoundly grateful to everyone. So thank you very much. And also, before I start, let me mention that I put up this little website with resources. So the lecture notes you'll find up there. And perhaps more importantly, there's a bunch of bibliographical notes. So in the talks, I'll of course mention, who the key people were, but it's hard to cover the details properly in a talk without breaking the narrative. So please refer to the website to see, who were the key people who contributed and what did various people do. There are some links to original papers and so on. Right, because this is, of course, a group effort. All right, so what we're going to talk about. So the main topic of these lectures, it's really one of the classical problems of numerical analysis and computational math. It's how do you solve the linear elliptic PDEs? So things like the Laplace equation, Helmholtz equations, the equations of linear elasticity. These things have been looked at for a very long time, obviously. Ever since we got computers, this has been one of the main things that they've been put to use to do. And there's been some even though it's a very mature field, there's been a lot of recent developments that at least I find very exciting, and I think they hold a great deal of promise. They're very well designed for modern computers. So computers today are designed very differently than they were 40, 50 years ago. So we've sort of taken a new look at these classical questions and come up with some different ways of doing things. But basically, when you take one of these classical equations, there are, in the literature and in current practice, there are really two paradigms for how to handle these things. So I've represented these by 2 columns. So there's a column on the left here. Some of you will recognize some of these early slides. So the left column is what happens if you take the PDE and you directly discretize it. So you take a partial differential operator, it's a local operator, you discretize it somehow, you apply it to some sets of basis functions, a finite element space typically, and then you're up with a very large sparse matrix. This system, and then you need to solve a linear system, Ax equal to b. The difficulty here is that the original operator is unbounded. So if you discretize it faithfully, necessarily the system matrix you end up with has to be ill-conditioned. Its eigenvalues, the singular values, have to span a very large dynamic range, which causes a bunch of numerical problems. But it's quite well known in certain environments how to accelerate convergence. Nevertheless, you can use iterative solvers to solve these systems. So you have a system Ax equal to b, and there exists a range of methods for solving these by successively applying the matrix A to a sequence of vectors. So things like GMREFs and conjugate gradients and things like this. So these methods, when they converge well, they have linear complexity because they involve a sparse system matrix. So doing a matrix vector multiply takes only n operations, O of n operations. And then if you get rapid convergence, you get linear complexity. There are also, classically, so since these methods are sparse, since the matrices are sparse, you can also, if you choose the pivots correctly, you can apply brute force Gaussian elimination. And you can do better than the standard n cubed complexity. So in 2 dimensions, you get n to the 1/2 complexity. In 3 dimensions, you get n squared, typically. All right, so that's an extremely brief summary of finite element methods. The other paradigm is to take your differential equation and you convert it to an integral equation somehow. And this has a number of advantages in that integral equations are more benign mathematical objects. And this is really the first lecture today is really going to focus on the niceness of the solution operators and of integral operators in this context and contrast that to the behavior of differential equations. So in any case, so if you can rewrite your problem, if you can formulate it somehow as an integral equation, ideally a boundary integral equation that's defined on a surface, in this case you can discretize it. You then end up with a dense system, which is a major algorithmic difficulty. It's much more expensive to deal with dense matrices than sparse. The saving grace here is that the system size can be smaller because sometimes you get a dimension in reduction. Sometimes it's easier to use higher order methods. You can use fewer degrees of freedom. But it's still a challenging computational issue. How do you handle these dense matrices? And in the 80s, it was discovered how to do fast matrix vector multiply. So even though the matrix in principle is a dense matrix with n squared elements, you don't need to explicitly form it. You can form a matrix vector multiply involving this matrix in linear complexity. So there are things like the fast multiple method, which is the topic of the second lecture today. So that's the second point we're going to do. And sort of to simplify slightly, the overall objective of what we're going to do this week is to construct direct solvers for both of these environments with ideally linear complexity. In some environments, we do have linear complexity. In others, we have not quite linear complexity, but typically good practical performance. Right, so let me mention here that when I say direct solver, sometimes in numerical analysis, the term direct solver more or less implies that you're using some version of Gaussian elimination, so that it's exact up to floating point arithmetic. That's not what I mean at all. So when I use this term, what I mean is that it's a very numerical sense, that if you give me a computational tolerance, say 10 to the minus 10, then the algorithms that we're going to devise, what they're doing is that they're constructing some sort of approximation to the inverse of the linear system. Or sometimes we don't even form this linear system directly. You directly construct an approximation to the solution operator of the underlying PDE. So now the solution operator is always a global operator. So of course we're not constructing the matrix explicitly. Instead, we're constructing it in some sort of data sparse format. So typically these operators, they tend to have the property that when you discretize them, their off-diagonal blocks have low rank. And you can exploit this to store them very efficiently. So the objective is, given a tolerance, I want to compute some sort of effective representation of the solution operator, ideally in linear time. And I'm not going to be super careful. When I do this sort of overview talks, I'm not going to be super careful about differentiating between computing an inverse and computing a factorization. Because even when I say I compute an inverse, what I'm actually computing is some sort of telescoping factorization. It's a compact representation of the operator. So take things with a slight grain of salt here. Right. So instead of computing an inverse, you might want to compute an LU factorization or something like this. And it's basically the same techniques are used in both cases. All right. So why do you want to do this? So one reason, a sort of simple reason, is that in many situations, you want to solve the same equation for a sequence of different data functions. So a classical example here is scattering. Let's say we want to determine the radar scattering of an aircraft. Then typically you're given a specific geometry. You're given an aircraft geometry, and you want to find how it reflects incoming waves for a bunch of different incoming waves. So in this case, if you compute the solution operator once for this given geometry, doing each successive computation after that becomes very, very fast. So similar things attain when you do optimal design, say. Say you're designing an antenna or an engine block. You have a basic geometry. And then as you modify things, you typically only do smaller modifications to the geometry at a time. And then if you have the solution operator for the original geometry, it's typically quite easy to update it. So I'm hoping that in that context, we should be able to do sort of real-time simulations for even complicated 3D geometries. Another reason, which is perhaps even more important, and this turns out to be a more persuasive argument when you're trying to get funding for these things, is to point to problems that even though techniques for solving elliptic PDEs, it's a very mature field, there are certain problems that still are very, very difficult for existing methods. So in particular, scattering problems. So I'm going to circle back to scattering pretty frequently during these lectures because it's one of the, in the context of elliptic PDEs, this is one of the really hard, outstanding issues because it's very hard to design good iterative solvers in this context. So this is nice. In certain situations, we'll be able to solve equations that really cannot be solved with existing methodology. And then there's a bunch of other reasons. So one thing you can do once you have direct solvers is you can do things like operator algebra. So you can glue different solution operators or different parts of a region together. I'm going to return and explain what I mean with that in detail. And then something that's work in progress, I'm not going to cover it in these lectures, but one of the objectives of this effort is also to compute partial spectral decompositions. So if you can compute an inverse, then if you look at methods for computing eigenvectors and eigenvalues, they're often based on things like shifted inverse iteration and so on. So if you can do matrix algebra, then at least our hope is that this will lead to efficient techniques for computing partial spectral decompositions. Right. Let me show some applications. So now there are some subtleties here. So it turns out that this was not really the main objective in starting this research effort, but as we've gone along, we've discovered that they actually have a bunch of other interesting uses as well. So one thing is that they can be used for numerical homogenization or numerical coarse graining. So suppose we want to model something like a composite material. So there exist a bunch of techniques for doing this, homogenization, multi-scale finite element methods and things like this. But I believe that the direct solvers allow you to do some interesting things here. So for instance, you can handle situations that are very challenging for finite elements, for homogenization, I should say. So things like a crack propagating through a composite material. They've turned out to be, again, somewhat surprisingly perhaps, they've been very useful for designing methods for dealing with corners. So this is an example from Alex and Adrianna, where you're looking at scattering at these really very irregular scatterers. And it turns out that direct solvers are quite handy in this context. We're going to do 3D geometries. And then here is this point about operator algebra. So again, this is work from Alex and Adrianna. So what this shows is it's an external wave hitting a photonic crystal with a little waveguide in it. And the operator algebra here, what I mean is that we're using a method for so a discretization that can handle PDEs with variable coefficients inside the crystal. And then it's a free space scattering problem. So when it leaves the domain, it goes off into infinite space. So we're using a boundary integral equation formulation for the exterior domain and a variable coefficient formulation for the inside. And then once you have a direct solver, it's very easy to glue these two things together. But of course, in classical numerical analysis, there are things like finite elements and boundary elements, couplings, but if you're trying to solve them with an iterative solver, it really turns out to be quite challenging. And then, you know, we're not militant. When we can design better iterative solvers, we're very happy to do so. So something else you can do direct solvers for is you can use them locally. So you can use them in small parts of the domain, and then use iterative solvers to solve the global dynamics. And I'm going to illustrate with solving a scattering problem in this geometry, and I'm very fond of this geometry because this is a sort of famously difficult problem in scattering. So you have a wave coming in hitting these guys, and there are two difficulties. One is that there are many bodies, so as the wave scatters, it bounces back and forth. And then the even more severe difficulty is that these things have cavities. So the wave energy goes inside these guys, and they bounce around a lot before they leave. And this is really very challenging to classical iterative methods, but by using a little bit of direct solvers, you can actually resolve this issue quite nicely. All right, so now I'm going to hold off on the flashy slides for a bit and talk about very basic math. So some of you are going to be very bored now for a little bit, because I'm going to just review some classical techniques for solving basically the Laplace and Poisson equations. And I'm perfectly aware that most of you have seen this, you know, undergrad PDEs. But I want to just point out some properties of the solution operators. So I'm going to show a couple of situations where we can analytically build a solution operator. I'm going to point out certain properties of the solution operators. And these are things that we're going to exploit later when we numerically construct them. Okay, so the idea here is that if you take something like the Poisson equation with some body load and some boundary data, then mathematically, okay, so suppose this problem is reasonably well posed, which it typically is. Then there's a unique solution operator. It's a linear equation, has a linear solution operator. And the point is that the map here that maps the input data G and H, lowercase, to the solution is very, very nice. So in particular, it's a smoothing operator. If you throw in something that's a little rough, if, say, the body load G is a little bit rough, then the solution U is nicer. It has two more derivatives, basically, which makes it much easier. It's a much nicer task to approximate this operator than approximating this operator. But if you throw something that's a little rough at the Laplace operator, what you get out is really quite a mess. Another obvious advantage is that this is a bounded operator. So if you think about the task of approximating with finite dimensional operators, it's a much more tractable job. You can actually have convergence in a strong sense. Whereas if you're approximating a differential operator, you have to talk about very indirect modes of convergence. So maybe convergence in the sort of low frequency part, but then you have to define what's the low frequency part. You have convergence of the inverse of the operator, but then what about conditioning? If the original problem is very ill conditioned, then, you know, how do you actually solve it? Issues like this. And of course, this generally is a very stable operation. The solution operator is stable. Okay, so the point being that the solution operators are generally more tractable. So let's do a specific example. So let's do the free space Poisson equation in R2. So as you know, we can move to Fourier space. So if we introduce the continuous variable Fourier transform, then the differential operator in Fourier space turns into just multiplication. So differentiation in physical space is multiplication by a polynomial in Fourier space. In this case, for the Laplace operator, the polynomial is very easy. It's just the absolute value of t squared. So the PDE turns into a polynomial equation. We can solve it very easily, like this. And then you just apply the inverse Fourier transform, and here we have an explicit solution formula. All right. So this solution formula, it's not super clear what it's doing intuitively. So let's try to move back to physical space. So we know that multiplication in Fourier space corresponds to convolution in physical space. So we have this formula. So U now is the inverse Fourier transform of the inverse Fourier Laplace operator times the body load, the Fourier transform of the body load. So multiplication in Fourier space corresponds to convolution in physical space. And then we get simply convolution of this guy with the body load. And of course, it's well known what this is. So this is what we call the fundamental solution of the Laplace operator. So it's something that has a very weak singularity at the origin. It's the log function. So it has a weak singularity at the origin, and it's very nicely C infinity away from the origin. So then we can write the solution as a convolution between this fundamental solution and the body load. That should be a G. That's a typo. Okay, so now let's think about this a little bit. So the first observation here, it's nice, and this is well known. You know, in classical numerical analysis, this has always been used, that the solution operator, it gains you two derivatives. So it's moderately smoothing. But the thing that has been used much less, which we're going to exploit much more directly in building direct solvers, is that over distances, and I'm going to make this precise in a moment, the solution operator is extremely smoothing. Okay, I'll show some examples to mean what I mean, to illustrate what I mean by the fact that it's extremely smoothing. But basically, if you have two separate domains, and you have the body load restricted to one domain, and you're looking at the solution in a different one, then it's basically always a C infinity solution, which can easily be approximated by series expansions. All right, so the final part here, what is not so nice, and what is the reason why there were very intelligent people who were designing, you know, finite difference methods and finite elements methods back in the 50s and 60s, but they were not really thinking about approximating the solution operators because they lead to dense discretizations. And this was completely infeasible back then. And they had so little memory that storing more than a few floating points per degree of freedom was essentially intractable. Like, it was not even, no point in even thinking about it. But this is something that's not so nice about direct solvers. They do require more memory. And this is really why it's only really very recently that these have become possible at all. All right, so let's do a simple example. So let's solve the Poisson equation with the body load being just the indicator function of the unit circle. If you look at the solution, it looks very nice. At this level of resolution, it almost looks like a perfectly smooth solution. It's not, of course. That if you differentiate it, this is what you get. And now you see that you have these lines where the derivatives are continuous, but the second derivatives are not. So the original function here is piecewise continuous. The solution is C1. But notice that if you look a little bit away from this line, that the only part where the solution is not perfectly nice is exactly where the body load is discontinuous. So there's one part that's fairly nice, which is the closed term behavior. You gain two derivatives there. But away from that part, it's really extremely nice. And you can express this precisely. There are many ways of doing this. What you can do is you can take your fundamental solution, just smooth it a little bit. You just sort of sandpaper off the singularity. And then you get a global operator, which is convolution with the C infinity function. And then you get a locally supported operator that's just moderately nice. That's the one that has the gain in two derivatives. And now the observation here is that if you can handle this one, the global part, then you're really mostly done. Because in a modern computing environment, any operator that's local is essentially for free, because flops are very cheap. It's communication that's expensive. So for this local part, it takes a little bit of work. You have to think about what to do with it. But it's essentially always a tractable problem. All right, let me hammer this point home. So let's do, we're still looking at the same equation, the Poisson equation in the plane. Suppose now that I isolate two rectangles in the plane. And I put some point sources in one, and I'm looking at the solution in another. Now I apply some body loads at these. Maybe it's not visible in the back, but there are 5 little dots in the red square. So the point source is there, and this is what the solution looks like. And it's truncated, so you have log singularities. At these point sources, the solution goes to infinity, and it's fairly irregular over here. It's still nicer. You have gained 2 generalized derivatives, even in the red region, but the point is that in the blue region, you're doing extraordinarily well. This is what the solution looks like if you restrict it to the blue region. Let's zoom in. It's very, very smooth. For a different particle distribution, it looks like this. And it's an analytic function here. You can very efficiently expand it using harmonic expansions. And we're going to do that in just a moment. All right. And I'm going to beat on this point because it's one of the core points. Suppose we put more sources in, make things nastier in the red part. Well, that does make the solution nastier in the red part, but it does nothing to make the solution nastier in the blue part. The blue part was still very, very nice, like this. All right. So now let's see if we can prove this mathematically. And this is a little bit to prepare for the next lecture, which is on the fast multiple method. So I mentioned a couple times that the solution, so the setup is the same. I put sources in the red rectangle and the red square, and I look at the solution in the blue square. Okay, so the operator that maps my given source distribution to a potential looks like this. It's an integral operator with this logarithmic kernel. And I notice that the x's are restricted to the blue box and the y's are restricted to the red box. So the kernel is very, very smooth, which means that we can expand it. And for the purpose of this expansion, it's very convenient to temporarily work with complex variables. So we write the logarithm using complex variables, and then we consider the complex valued potential evaluation map. Just take the real part of this and you return to that. All right? Now, for this logarithmic kernel, we can expand it very nicely. So what we do is that we extract the dominant part. So the geometry is this. I have my sources. Here's the center of the source domain. Now x is some vector out here, and y is a short vector inside the source domain. Okay, so I extract first the dominant part, so the log. So log x minus y, expanded about c. So first approximation, it looks like just the plain log function itself. But then there's a small correction. So here's the correction. Once I've extracted the dominant part, I have this correction. So the green term here is a term that has modulus less than 1. Now we have a nice series expansion for small corrections to the log function. It looks like this. And we plug that in, and we get the following series expansion. Right. I'm assuming most of you have seen this before, but let's just do it in excruciating detail just to make sure. All right, so now what you do is you take this series expansion, you plug it in to the potential evaluation map, and you get the following expression. So now observe that the blue terms here depend only on x. They depend only on the target, whereas the red ones depend only on the source distribution. So you really split the computation into 2 parts. You start by processing the sources, and then once you've done that, you can very easily evaluate the potential. All right, so you get this sort of expression. If you make some very mild, modest assumption on G, for instance, that it's in L1, then you can say that these expansion coefficients are bounded, which will immediately tell you, notice that there's no assumption of smoothness in G. There's something very mild, just that it's in L1 is sufficient to say that you get rapid convergence here. And the rates of convergence really depends on the radius of the source region in the denominator, and in the numerator you have the modulus of x. So if you're some distance away, you get very rapid convergence here. So this is a multipole expansion. And in the next lecture, we're going to exploit this to great detail. If you're more comfortable looking at the real valued part, it looks like this. If you just take the real values of the expressions on the previous slide, it looks like this. You get a classical expansion in cosines and sines. We're going to stick to complex variables for the most part here. Okay, so that's really all I wanted to say about the Poisson equation. Now let's look at its close cousin, the Laplace equation, just to see what happens if you have boundary data instead of body loads. So the situation I'm looking at is a simple geometry. So we have a circle. Omega here is a circle. I specify Dirichlet data for the Laplace equation. And then in this case, it's a nicely separable domain. You separate variables. So again, using polar coordinates is very convenient. And then you take just the Fourier series of the Dirichlet data, and then you can directly identify, basically by inspection, you can write down the solution here. And the point here is that, again, basically regardless of the smoothness of the Dirichlet data, if you're looking at the solution in anywhere sort of in the interior of the domain, just a little bit separated from the boundary, it's extremely smooth. It's, to be precise, it's analytic. So this radius is 1, and if you restrict the solution to some disk, just a little distance epsilon away, then the solution is analytic. It's C infinity with a known expansion in polynomials, really. So you have an exponentially rapidly convergence polynomial expansion of the function, which is about as nice as you get. Right, so just let us massage this expression a little bit, just to introduce some more useful mathematical things. So what we can do is we can introduce a Green's function. So let's see what's happening here. All right, so here we have the solution formula. So here's the expression for the solution. Now what we're doing is we're plugging in the expression for the Fourier expansion, the Fourier coefficients of the Dirichlet data. And then if you interchange summation and integration, you get the Green's function of the problem. So there's a Green's function, G, that has two variables in this case because of the symmetry of the problem. And the solution now is simply a convolution of the Green's function against the Dirichlet data on the boundary. So the point here, why I wanted to raise the Green's function, is that I wanted to be able to show a plot of it. So this function, it's extremely nice. Again, it's analytic in the interior of the circle, and then it has this one singularity at the outside. So you convolve with this singularity. Of course, it has to be singular out here, because if you restrict it to the circle, then it basically has to be the delta function, because you're given Dirichlet data, so the solution has to equal the Dirichlet data on the circle. So again, the point I'm trying to come back to again and again is that you have some localized, mildly unpleasant behavior. But away from there, these are all integral operators with very nice smooth kernels. So they're easy to approximate. All right, if you have a general domain, then, or if you have variable coefficients, then everything I've said in principle holds true. That, exact statements about how smooth things are and so on change. But conceptually, you still have a lot of smoothing over distances. And the only difficulty now is that we don't know the solution operators exactly. So the only cases we explicitly know these Green's functions, and the fundamental solution is if you have constant coefficients and a very simple geometry. You know, you have the entire plane, you have a circle, you have a square, something like this. If you're given a general domain, a variable coefficient problem, we don't have analytic expressions, and the objective of the direct solver endeavor can really be said to be to construct these numerically, while exploiting the fact that we know a priori that they are going to be nice for the most part. All right, so just to give a very brief connection to things that Alex is going to talk about this afternoon, so something you can do. So for instance, if we look at the Dirichlet problem on a more general domain, then you can actually exploit a lot of the things we've So we had a discussion now about the niceness of the fundamental solution. And if you read up a little bit on potential theory, you'll quickly find that you can actually, there's a representation formula, that the solution to this Laplace-Dirichlet problem you can write as an integral of some unknown distribution that lives on the boundary. So we're given some domain, omega, with a boundary gamma, and there's now some charge distribution on the boundary Q that has the property that it induces the solution U when you convolve it with the free space fundamental solution. So the gain now is that I use a known kernel in the integral. The loss is that now I don't know Q. But the whole point of rewriting things as boundary integral equations is that you can, once you have representation formulas like this, you can quite easily get an equation for the unknown Q. You can solve that, and then you can use a lot of the techniques that I just hinted at, you can use to show regularity in U, basically. Okay, so 4 techniques on how to determine Q and so on. Alex will talk about it later today, and I will return to this on Thursday. Okay, so this actually went a little faster. So what I'm going to do is I'm just going to continue to talk about fast multiple methods. But let me just wrap up the main points here. So yeah, now I'm starting to repeat myself a little too much perhaps, but let's just take it slow to begin with. So the point here is really just that solution operators of elliptic PDEs are very, very nice. And something I haven't mentioned earlier is that these things, you can typically represent them in hierarchies, which parallelize very well. So a difficulty of solving PDEs with iterative methods is that, think about it in principle. So at first blush, suppose you discretize a PDE. So you get some sort of finite difference matrix or a finite element matrix. It has a very small support because it approximates a local operator. So in principle, when you apply the matrix, you can really only propagate the solution a tiny amount. If you give it some initial guess, the second guess can really only move information about a couple of grid spacings. So in principle, and of course, elliptic operators, they're global. The solutions, if you change anything in any part of the domain, the solution changes everywhere. So in principle, you need to step. The number of iterations you need is really the diameter of the domain. Of course, in principle, it doesn't work like this because people do exploit known properties about these operators. So they know that if you represent them in some sort of multi-scale representation, so multigrid, for instance, you look at not only the grid on the fine space, but you look at a whole hierarchy of grids. So there's some sort of conceptually very coarse finite difference operator at the top level that spreads information quickly. And then you go up and down. But doing this kind of thing, you either have to know really a lot of the problem in advance. So multigrid works very well for simple situations where the solution operator, you sort of roughly know what it looks like in advance, something like Laplace equation. For more complicated equations like scattering, you really have no idea what the solution operator looks like, and in that case, multigrid does not work so well. So but basically, the point here being that when you use iterative methods, you have to go up and down a tree many, many times. And this is quite costly on a parallel computer. The direct solvers we're going to construct, they really, I'm simplifying slightly, but for the most part, they're all based on hierarchical trees. And oftentimes, it's only a very small number of passes. So you build the solution operators. It's oftentimes just a single pass from the finest levels of the trees to the top. And then you have all the solution operators. So of course, it's a more expensive pass than a single pass in an iterative solver, but it's just one pass. So there's less communication. Yeah, so the main difficulty here is that operators are global, and the way we're going to get to better scaling is to exploit what I refer to as smoothing or information loss over distances numerically, what that's going to translate to is that the matrices have off-diagonal blocks of low numerical rank. Okay, so let me actually just transition directly to the first multiple lecture.
Do you want to take questions about this?
Yes, that's a good idea. I should have said that.
No one's asked anything yet.
Yes. So 2 things. I will, and Alex will help me, periodically explicitly ask for questions, but in addition to that, you're of course extremely welcome to ask questions at any time. This is a very informal setting. But so now let me explicitly take a pause and any questions? No.
I'll start.
Ah.
So if I try conjugate gradient solvers with some sort of preconditioner on a big Helmholtz or a big elastic finite element elastic wave equation, I can get it to converge, but it's lost in the high frequency solution. It's converged to a very nice answer, but I don't have the high frequency information. So the question is all right, I used a conjugate gradient solver. I used an iterative solver. And if I try and do it with a direct method, it's intractable. It's 10 to the 7th, and it's just, it's 10 to the 25th operation or something, and I can't do it. So what do I do? I mean, how can I want to solve what I want to do is I want to solve with a direct method on a coarse grid and get a good answer. And then extend the coarse grid solution to a fine grid and get the details. But I don't know how to do that.
It might be most so this is a deep question. It has lots of different parts.
I know.
Yeah. Perhaps this type of question would be more productively addressed later in the week.
I appreciate that too.
Right. So roughly, so there are 2 issues. So one is discretization. So in principle, so if you discretize, if you use a good discretization, it should be faithful. It should, the solution to the discrete problem should be very close to the solution of your mathematical equation. And that in principle is unrelated to the solver question. So if you use an iterative solver, if you do have convergence, you should in principle get what most people mean in that statement is that the residual in the equation you're solving gets very small. So, when an iterative, so this is actually a critique I would not make of iterative solvers, that when they converge, they're great. There's nothing wrong with an iterative solver. So if you get an error, that's really something that's more related to discretization, I would say.
Yeah, I agree.
So the question of discretization is a little bit different. It's something I have not touched on in this lecture, and I'll touch upon it a little bit, but the focus here is really on the solvers. So another just quick comment that your question allows me to mention is that so the very interesting question here is about different scales. So in wave problems, so typically at scales that are larger than the wavelength, all these sort of multi-scale tricks like multigrid don't work very well because the solutions are idiosyncratic. For any given geometry, the solution operator has sort of complicated behavior that depends on the geometry. And this is precisely what the direct solvers are designed for. Then for the sub-wavelength scales, you can do a variety of tricks to accelerate solves. It turns out the direct solvers are actually fairly fast in that regime, so you might as well use them there as well. But yeah, what we're all going to circle back to is for things that don't have oscillatory solutions, a variety of techniques work. Some work better in certain environments, and I'm going to discuss that. But the thing that always remains challenging are wave propagation problems over domains that are many, many wavelengths. We're making, with direct solvers, we can address some problems that are inaccessible to iterative methods, but certainly not the panacea. There will remain many challenges in that regime. Sorry, I'm avoiding your question slightly, but it's for a reason. No. Okay. So let's proceed to the fast multiple method. So this first day, it's going to be a little bit curious. You know, the first lecture was very slow. It's concerned undergraduate PDEs, basically. You've seen it. The second lecture will be very fast. And the reason for this is that...
Wait, don't go too fast compared to what you just did.
Okay. Yeah, it's just that, you know, I want to cover the fast multiple method in large part to familiarize you with my notation and the way that I talk about things. I'm sort of mildly assuming that most of you have some familiarity with fast multiple methods. If not, you might want to, if not, then two things you should know in advance. One is if you read up on as I posted on the web page, there's a link to a tutorial it's an encyclopedia article actually, it's like 9 pages long. If you read that, that will fill in the gaps. And the second part is that this topic, it has certain complications that aren't really present in the direct solvers. So there's going to be a lot of lists, things like interaction lists. So you have a tree of boxes, and there are ways of keeping track of long-range interactions. And it's a little complex. But if you haven't seen it before, you find the slides confusing, you actually don't need to bone up on it this afternoon. It won't come back. For the direct solvers, interactions are much more close range. They're very precisely for the reason that they have less communication than fast multiple methods. So, you know, this is a very nice set of techniques. I encourage everyone to study them. But it's not the case that if you feel a little bit lost at parts of this lecture, that you're doomed for the rest of the week. It's really, yeah.
Also, the slides are all online. You should
yes.
All of Gunnar's slides are online, so you can go and check. You don't have to write everything down.
No, absolutely.
You can read the slides later again.
Yeah. Okay, and let me also remind you about the bibliographical notes. So for the FMM, it turns out to be very easy, because foundation work was done by Greengard and Rokhlin, some other key work was done by Rokhlin alone, and these are really the key references. But nevertheless, there's a bunch more details on the web page. So we're going to look at a very superficially quite simple problem. So we're given n point charges in a domain. So the geometry now is we have one domain, n charges. They all talk to each other. At each point, we're given a source, qj, and I want to evaluate this sum. So there's a sum here that involves n squared pairwise interactions. The kernel is the same one from the first lecture. It's the log x minus y. I'm going to use the fact that we've already derived a series expansion for log. So for the most part, we're going to use complex notation here. We're thinking of points as complex numbers. Right, so the issue is evaluating this sum. And I'm going to start by looking at a much simpler problem. So the main difficulty here is that what I call the sources and the targets. So the sources are where I place charges, and the targets are the points where I want the potential. So the difficulty here is that they're the same. Let's start with a much easier problem. So suppose that the sources are confined to a little box. So we're now back to precisely this geometry. And suppose I'm only interested in targets that are away from the box. So they're well separated. So they're in a box whose side length is really 3 times the size of the black box. Okay, so I'm given the 2 locations. This is the sum I want to evaluate. You can view this as a matrix vector multiply with a matrix of size, a dense matrix of size m times n. And the cost is, of course, O of mn. But in the previous lecture, we derived a separation of variables. So I can write this, the kernel here, log x minus y, as a series expansion, where each term in the series is a product of something that depends only on the target location, that's the blue factors, and something else that depends only on the source locations. That's the red factors. All right. So this is so these things arise all over potential theory. and they're called separation of variables. And for these to be useful, you have to have reasonably rapid convergence. And in this case, we do. So you take this series expansion, you plug it in up here into this expression. On the last set of slides, we had an integral, and then we interchanged summation and integration. Now we have a sum. Of course, doesn't really make a difference. You interchange the two summations, and then you get the following expression. So if you look at the target domains, if you look at the target points, so to first approximation, the field looks really just like a log. So the field looks as if you put, so q hat 0 is just the sum of all the sources. So to the first approximation, you sum up all the sources. That gives you what's called a monopole moment. And you approximate the field by putting just a single source here. The second term is a dipole term. So now you take locations a little bit into account of the sources, and that will somehow give you a dipole moment. So that's the second term. And then it continues up like that. So convergence now, as I mentioned, it's exponential. So it depends, in this case, I call a side of a box to be 2a. So this distance is a. That means that r here is root 2 times a. And I restrict targets to a box that's 3 times as large. So this is big R, which is 3a. So if I restrict my target locations to be far away, then I have exponential convergence, and the rate of convergence is this. So it's root 2 divided by 3. Okay, so this allows me to fix a p. So the idea here is you give me a tolerance. Say you want an answer to 10 correct digits. And then you just crank up p until this expression is 10 to the minus 10. What is that? Is that p equal to 30 or something? Something like that. Yeah. And then you truncate the term. You truncate the series expansion. Oh, that should be a p. Right. So now what are the costs? So you need to evaluate the multiple moments, which are these q hat p. And here, each source has to communicate the information to each one of the multiple moments. So each one of the source points contributes to p plus 1 expansion coefficients. So this cost is n times p. Then once you have all the expansion coefficients, the cost of evaluating a potential given a point x is m times p, because now you have to evaluate, for each target point, you have to evaluate the field from each of the p plus 1 expansion functions. So the point here is that we've gone from the multiplicative cost m times n to cost p times m plus n. Right. So this is nice, but this is just classical separation of variables. You know, this is not a fancy algorithm. This has been known for a very long time. And so the one reason I wanted to go over the fast multiple method is that I wanted to talk for a while about things that I'm hoping is familiar to most of you. To introduce it, so I want to cast a lot of these things as linear algebra. So I like thinking of things as matrices. This was greatly confusing, by the way, when I started working with Vladimir Rokhlin, because he much prefers to think about the physics, and I prefer the linear algebra. But it's good to be able to think about it both ways, because sometimes one way is more powerful, and you know, at least to me, sometimes thinking about it as matrices is helpful. So if you think about what I just said in terms of matrices, then doing the potential evaluation really corresponds to multiplying by a dense matrix. The multiple expansion corresponds to a factorization of this matrix. So A is exactly equal to a factorization where P is infinity. Okay, but that's not very useful. That's very non-useful from a numerical point of view. But the point is that you have exponential convergence. So you can stop after a very moderate number of terms. If you stop after 20 or 30 terms, you get very good accuracy. All right. So that's thinking about things as a matrix multiplication. Another way that we're going to use to illustrate things graphically is to view this as commutative diagrams. And when I say that they're commutative, I mean that they're commutative to finite precision. So the map A directly takes the vector of source location and maps to the vector of potentials. Then the multiple expansion you can view as multiplication by C, which is going from a potentially long vector Q down to a short vector Q hat. So Q hat has just P terms. So this is multiple expansion. And then you do evaluation of multiple terms going from the multiple expansion to the potentials. Right. So point being that it's cheaper to go the lower route.
One question.
Yeah.
What does the tilde indicate? Is there a notational implication? Maybe not yet.
Yes. This is, what I'm showing here is it's a very condensed version of a fuller description of the fast multiple method. So B tilde has, from the point of view of the fast multiple method, this B tilde is unfortunate because it depends on all sorts of things. It depends on the precise target locations and on the center C. So it's a slightly unfortunate operator. It will be eliminated in the proper fast multiple method. So it will be replaced by a B. So it's, the reason for it is laziness on my behalf. I didn't want to develop a totally new notation. And no. To be honest, it's also that, then when you read, you can take this and then you read the tutorial or the encyclopedia article and the notation will be the same.
Okay.
Right. All right. So as a general matter, something that is standard though for me is that I put hats or tildes on short variables. So I have long variables that are unadorned, and then things with a hat or a tilde is compressed version somehow of that variable. All right. So let's define the concept of well separated. This will feature prominently in the fast multiple method. So this refers to locations in reference to a box. So if we're given a box omega, then locations that are well separated with respect to omega are locations that are outside of a box, concentric box with 3 times the size. So these blue points are well separated from omega, the red points are not. So what it means to be well separated is really that multiple expansions converge at the prescribed rate. So remember the path here that you give me a tolerance. Once I have a tolerance, I pick a P that will assure that the multiple expansion is accurate to within whatever tolerance you give me. And then well separated really means that this is the region where it's safe to use the multiple expansion instead of direct evaluation. You're guaranteed to do things within the prescribed tolerance epsilon. And then multiple expansion, or I'm going to use the term outgoing expansion. So essentially, most of the work I'm going to describe this week, it's intellectually inspired by the fast multiple method. So in the literature, we often call things multiple expansions. So compact representations are oftentimes called multiple expansions, even though they haven't. These days, oftentimes they have nothing to do with multiples. It's just some very vague intellectual connection. So I'm trying to rectify this by using the term outgoing expansions and incoming expansions to signify that these things can have a much broader sense of meanings than just multiple expansions. But I won't promise to stick to it 100%. I might sometimes slip and say multiple expansion. Okay. So in any case, the multiple expansion for a box, if you're given, or an outgoing expansion, if you're given the box, you're given source locations in it. So you have source strength and locations. There are 2 pieces of information. So you encode that into this sequence of expansion coefficients. And that sequence of expansion coefficients is the outgoing expansion. So I denote that as the vector Q hat. All right. So let me just do a not very clever and moderately useful slightly accelerated algorithm before the break, and then when we come back, we'll do a more sophisticated algorithm. So now we return to the original problem we started. So remember that for the last 10 minutes, I've talked about this simplified problem where I'm given a set of sources that are well separated from the set of target locations. So this is the easy case. Now let's return to the harder case, where you're given a set of points and there are sources at all points, and I want the potential at all points. So now I cannot just plainly do multiple expansion, of course, because there's no convergence inside the box. So what do you do? And what you can do is we can subdivide it into smaller boxes. So we do some sort of divide and conquer. So I'm assuming that the particles are more or less uniformly distributed. I partition the big domain into smaller boxes. Now there's some tuning parameter, little m, which I'm free to choose. This I can optimize. So I put about little m particles in each box, and then I get big N over little m boxes. Then, as I mentioned before, given a tolerance, I pick a term p that tells me how many multiple coefficients do I need to keep to meet the requested precision. And then for each box, I compute the outgoing expansion. All right. Now, suppose I seek the potentials at these blue points. What do? Well, some of these boxes are now well separated. So from the point of view of the blue box, all the boxes with a single red dot in them are well separated. So for all of those boxes, I can safely replace, I can forget about the particle locations, and I can use just the multiple expansion. So use the multiple expansion centered around the center of each one of these boxes. And that will accurately communicate their contributions to the potential inside the blue box. Right. For these guys, where the original points are still shown in this figure, the multiple expansions are not valid. So here I just have to bite the bullet and by brute force evaluate all pairwise interactions. So again, you can now see this connection. That's really what I'm solving here is the Poisson equation, right, with a bunch of delta functions at the locations. So I'm sort of doing numerically now this splitting into a moderately nice close-range computation and a smooth, nice long-range computation. This is a very simple numerical manifestation of that split. Okay, so what's the cost? So now we have to think about how to pick this tuning parameter m. If you pick it too small, meaning that you have lots and lots of boxes, then there's no gain, because evaluating all interactions with the far-field boxes will be essentially as expensive as the original problem. If I pick m too large, there's also no gain, because then doing the close-range evaluations is basically an n-squared operation. So the golden point here is to pick root n points in each box. And in that case, you can see that all these different terms balance nicely, and you get basically n to the 1.5 operations. So we've gone from n squared to n to the 1.5. So we're on the right path, but we need to do better. And let's take a break, and then we'll return to that at 10:30.
Sounds great.
All right, thank you.